Thank you for the invitation to give the talk. My name is Reitz, and my advisor is Yaroslav Sirkovniak at UCLA. Today I'll be talking about a new theory that we've been developing over the past couple of years for nuclear spin-Seebeck effect, and I'll be applying it to a case which has been studied experimentally recently in antiferromagnets. So I'll be considering an antiferromagnet with nuclear spins inside the antiferromagnet. So introduction to spin-Seebeck effect. Basically, we'll be converting a heat source into a spin current, and then eventually out into a charge current, which is how we'll measure the effect in an adjacent metal. And we'll be considering insulating magnets here. So there's a magnetic branch here, and there's the nuclear spins. The key features are the nuclear spins can hybridize with the magnons, and the magnon branch is generally at a higher energy than the nuclear branch. So there's two types of spin. Actually, also one thing to mention, I'll be looking at low temperatures below the magnon branch, so that the nuclear spin-Seebeck effect is actually a significant contribution. So there's two contributions to the Seebeck effect in general. Thermal gradient in the bulk can cause spin current to be induced in the bulk and cause magnons to accumulate at the interface, which can produce its own spin pumping across the interface. There's also an interfacial effect just due to a thermal bias directly at the interface. So that's what will be driving our contribution here. So this would be a thermal bias between the magnetic carriers in the magnet and the electrons in the metal. So we'll be looking at easy plane antiferromagnets with nuclear spins embedded in antiferromagnets. But the first question would be, can we explain the data by just some ordinary electronic contribution to the spin-Seebeck effect? So for an easy plane, so that's what I'll explain first. So we have an easy plane antiferromagnet with U1 symmetry in the easy plane. So there's a high energy mode associated with rotation of the nail order out of the plane, but that's we're going to be looking at very low temperatures, so we can neglect that mode. There is a lower energy mode, which is the Goldstone mode associated with nail vector rotation inside the easy plane, and that is gapped by magnetic field. So we can calculate. So if there's an interfacial coupling between magnons or in general the spin carriers in the magnet and the electrons in the metal, then spin current can be transferred across the interface. And this magnon branch, for example, can produce a spin-Seebeck effect. So we can calculate the long wavelength, low energy contributions to the spin-Seebeck effect by just looking at the spin fluctuations at the interface, and then calculating the spin current, which is a 2-point correlation function, using the fluctuation dissipation theorem. That's pretty straightforward, been done many times, so we just kind of applied it to the antiferromagnetic case. But the key feature there is at low temperatures, temperatures comparable to the gap of the magnet, or even below the gap of the magnons, this antiferromagnetic contribution will be exponentially suppressed, and it certainly won't be increasing the field at very low temperatures. As for the hybridization contribution, there's hybridization between the nuclear branch and the magnetic branch. This is something that's well known, actually been studied in the 1960s to the 1990s for many years as nuclear hybridization effect. And that was the original motivation for looking at this thermal electric phenomenon, as a realization of this kind of hybridization physics. But it turns out that when you calculate the contribution to hybridization, to the Seebeck effect, it is also decreasing with magnetic field because the magnons are gapped with magnetic field. So eventually, as you go to up to a few Tesla, the magnetic branch is at such a high energy that hybridization is basically negligible. So hybridization only occurs with very small fields, and the data that I'm about to show is not consistent with that. All right, so the data here is from our collaborators, Yaji Saito's group in blue, and then the red curves are theoretical curves that we produced from our theory for the nuclear spin-Seebeck effect, which I'll explain in the remainder of my talk. So yeah, I would just like to thank our collaborators for these extraordinary experiments, doing a spin-Seebeck experiment at very, very low temperatures. This is data that is currently under review. The publication, along with the theory component, is under review, but should hopefully come out shortly. And now we're looking to apply our theory to other magnetic systems, because we expect it to be a general phenomena that could contribute to the spin-Seebeck effect at low temperatures. So as for this data, this is an easy plane antiferromagnet at ultra low temperatures. We see that we're going down to very low temperatures below 1 Kelvin with relatively large magnetic field. So here the gap especially the high magnetic field is orders of magnitude larger than KBT. So it's hard to imagine a electronic magnetic contribution, and especially at the very low temperatures, it's just not possible to explain the data, especially this increasing portion with magnetic field. We would expect the electronic magnetic piece to be strongly decreasing this field, and for the standard hybridization, like the nuclear hybridization piece here, that would also be decreasing the field and wouldn't be able to reproduce this non-monotonic dependence. Okay, so to explain the non-monotonicity, we instead looked at direct spin pumping by the nuclear spins. So that is accomplished via the Karinga relaxation. So if you're not familiar with the Karinga relaxation, this is the dominant way that nuclear spins relax in a metal, in the bulk of metal. So in Karinga's original paper, he considered NMR pulse that excites nuclear spins up to a higher energy state, and the relaxation, he described the relaxation of the nuclear spins into the Fermi seed. Here we have nuclear spins which are biased in a magnet that's connected to a metal. And the same type of physics can describe interfacial spin transfer. So it's in a sense interfacial thermalization of the nuclear spins with the temperature in the metal. So if there's a thermal bias, again, spin can flow across the interface through direct interfacial nuclear spin coupling, a hyperfine interfacial spin coupling. So the nuclear spin-Seebeck effect is the spin current requires a canting of the antiferromagnetic order, because basically the nuclear spins, their orientation, the polarization is determined by the underlying magnetic order in the magnet. And if there's no canting, then there's just adjacent nuclear sites which are oppositely oriented, and their contributions cancel out. So we need canting, so the effect is proportional to magnetic fields from that, and it's also inversely proportional to temperature from the Curie law, temperature dependence of the nuclear spin polarization. And then there's the factors of nuclear thermalization. So in thermal equilibrium, the energy going in to the nuclear spins has to be balanced by the energy going out into the electronic spins. So that the energy going in would be proportional to the temperature difference between nuclei and phonons, and the energy going out would be proportional to the difference between temperature of nuclei and the electrons. And then these proportionality factors are what we worked out in our theory. And so that was actually able to explain, this thermalization was actually able to explain the non-monatomic field dependence. So in a nutshell, at small magnetic fields and high temperatures, the electronic magnons are thermally populated, and it's kind of direct two magnon processes can thermalize the nuclear spins, and the magnons then couple to the phonons to spin orbit. So that provides a direct, very fast thermalization of the nuclear spins. So at low fields, the nuclear electron thermalization is what limits the rate of spin transfer. At high fields, the magnons are gapped out, and so it's instead virtual magnons which mediate the thermalization of the nuclear spins with phonons, because the nuclei are not, they do not couple to the phonons. They only couple through the hyperfine interaction to magnetic spins. So this is a very slow process, and in high fields, we end up getting the nuclear phonon thermalization rate being limiting the total spin current. All right, so that's basic explanation for the non-monotonicity here in the data. The nuclear SC is driven by the interfacial hyperfine interaction, and it may be present in any magnetic system where there is some hyperfine splitting of the nuclear spins, and interfacial hyperfine interaction with an adjacent metal. And this contribution is expected to be significant when magnons begin to freeze out. So with that, I'd like to thank my collaborators, the IG Cythos group, for allowing us to look at their data, and my advisor for giving me this interesting project to work on.